In this video, we're going to talk about the idea of least squares approximation. So here's the linear algebra setup for things. We're going to have a subspace W. We're going to have some vector that doesn't lie in W. We want to try to find the closest thing in W to U in some sense. So if we just think about dropping it geometrically, if we think about dropping the tip of U down to W perpendicularly, that's what we get. That's what we mean by the projection of U onto W, that vector that we get by taking this point and dropping it down perpendicularly. Then, of course, if we subtract those two vectors, that gives us the other side of this right triangle, and that's where we get the U minus the projection of U onto W. All right, so what we're going to show is that if W is any vector different from the projection, then when I take the magnitude of U minus the projection, that's going to be less than the magnitude of W. Now, in a Euclidean sense, this makes sense, right? All we're doing is trying to go as short as possible from this point down to W. So we know we can do that perpendicularly or orthogonally, if you will, from a linear algebra perspective. If we do any other vector that's in W, certainly if I take that line, it has to be longer than this side. And it certainly makes sense from a Euclidean geometry idea. However, not all inner product spaces are Euclidean, as we've seen several examples in previous sections. So we want a system that will work for our purposes here. We want a system that will work no matter what inner product space we're talking about. All right. So to show that why this is true in general, do our tried and true trick here of adding and subtracting the same quantity. Doesn't change the expression. We're going to take the magnitude of both sides and square it. Now, U minus a projection of U onto W is orthogonal to this projection of U onto W minus W because this is a vector in W and this is perpendicular to everything in W. So we get that Pythagorean theorem idea where I can split it up at that plus sign. And then I notice, I said we're assuming that W is any vector other than the projection. Well, that means that this is not the zero vector, which means that this is a positive quantity. So to get the magnitude of U minus W squared, I have to add something, not zero, something to the magnitude here. So that means that the magnitude of U minus W squared is greater than this magnitude, and then take the square root of both sides, and we see that U minus the projection of U onto W really is the shortest way to get from the tip of U down to W. All right. Why does this help us? Well, let's say we have a linear system, AX equals B, that's not consistent. So to get you into something that you may have seen before, think about having a whole bunch of points, a scatter plot, and you want to find the line of best fit through those points. Well, we know that once we get more than a couple of points, the chances that all of those points fall on the same line is pretty small. So if I try to plug those points into a line, formula for a line, and try to solve, I'm going to get an inconsistent system, usually. So instead of trying to find the line that goes through the points, which is impossible, we're going to find the best line in some sense. And that line is going to be the one that would make this expression, the AX minus B, thinking about subtracting the B to the other side, making this as small as possible, making it as close to the zero vector as we possibly can get. All right, so let's let W be the column space of A just for notational purposes. Then certainly if I take A times any X that I want, I get something that's in W. By the previous result then, we know that AX minus B is going to be as small as possible when I use the projection of B onto W for that AX. That's going to be the vector in W. That's as close as possible to B as we can possibly get. That was what we just mentioned on the last slide. All right, so to solve this system, we'll do B minus on both sides. We know that B minus the projection of B onto W is orthogonal to W, but remember that W is the column space of A. The column space of A, its orthogonal complement, the W perp, is the null space of A transpose. So that means that if I plug this vector into, if I multiply this vector by A transpose, I get 0. So if I take A transpose times B minus the projection of B onto W, I get 0. And then remember, for projection of B onto W, we mean B minus AX. That was what we were representing with a projection of B onto W as. And then if I distribute the A transpose through and rearrange, I get this system. So I have A transpose A times X equals A transpose B. This has a special name. This is called the normal system associated with AX equals B, and it has some nice properties. It's always consistent, no matter what. It always has at least one solution because we know that the projection of B onto W, which we can always do, solves this system. Okay, no matter what. That was what the work we just did. It's also always a square system because when I take A transpose times A, I get a square matrix. If A is M by N, A transpose is N by M, so I get N equations and N knowns in the system. So I have a square system. And we know some things about square systems, which we're going to use here in a minute. All right. It's also possible for the system to have infinitely many solutions. Probably the easiest example of that is that if the A is the zero matrix, then you get infinitely many solutions. It's possible to get infinitely many least squares solutions. Those are degenerate cases. We don't like those cases very often, but it is possible. So what we're interested now is, when do we get a unique solution? When does it always just A, not any least squares solution, but the least square solution? Well, certainly it'll be unique if I can multiply both sides by A transpose A inverse, because then I can get X by itself. So we know that this is going to happen exactly when A transpose A is invertible. So let's see if we have a theorem that tells us when that happens. All right, so A is going to be an M by N matrix here. Then A transpose A is invertible if and only if the columns of A turn out to be linearly independent. All right, so let's do the proof. It's not a bad proof. Let's say that A transpose A is invertible, and we're going to show that one way to do that is to show that the only solution to the homogeneous system is zero. That's one of the equivalent conditions to being an invertible matrix. I should have an A transpose. I'm sorry. We're assuming that it already is invertible. We're going to show that this system only has the trivial solution, and that will give us linearly independent columns. So if I start with AX equals 0, then I can multiply both sides by A transpose. But A transpose A is invertible, so I get X equals 0 at the end by multiplying both sides by the inverse of A transpose A. So the only solution to this equation, AX equals 0, is X equals 0. The only way that this can happen is if A has linearly independent columns. Because why? Think about why. Oops, let me go back. Think about why this has to imply that A has linearly independent columns. Remember, if A doesn't have linearly independent columns, then we get free variables when we do the reduced row echelon form. If we get free variables for the homogeneous system, that means we have infinitely many solutions. But we just said we don't have infinitely many solutions, we only have one. So the only way that can happen is if we had the columns being linearly independent. Okay? Think about it another way. You can think of this as a linear combination of the columns, and the only possibility that gives you the linear combination of the columns to be the zero vector is if you started with zeros for all your coefficients. It's another way to think about it. Let's go the other way. Let's assume that A has linearly independent columns, and my arrow should be pointing the other direction because I'm proving the other direction. All right, so now let's suppose that A transpose A is 0. All right, by supposition, AX is in the null space of A transpose because I've set up with A transpose times AX equals 0. So AX is in the null space. That's the definition of being in the null space. It's also in the column space because when I take a vector times a matrix, that vector that I end up with is a linear combination of the columns. Plus, we know that the column space and the null space are orthogonal complements of each other. The only thing that's in both then at the same time is the zero vector. So we have AX equals 0. And if this is the only possibility for your solution, then we have, let's try that again. This is the only possibility for solution. We're assuming that A has linearly independent column vectors. Therefore, X had to be 0. If X has to be 0 up here, then this original equation only has the trivial solution, which means the matrix A transpose A is invertible. Anyway, that was the whole point that we wanted to get to, was that as long as we have linearly independent columns of A, we're going to be guaranteed a unique least squares solution. As long as we have linearly independent columns, we'll get a unique solution. Okay? What does that solution look like? Well, since I can take the inverse of A transpose A now, I get the least squares solution simply by taking the inverse of that matrix. So the least squares solution X is going to be A transpose A, do the inverse of that matrix, multiply it by A transpose, and then multiply it by B. This is always going to solve our least squares problem as long as we have a linear system of equations to start with. So this is what we'll talk about in class, about how to solve these problems. We're not going to go back through this proof again, but this is the formula that we're going to use to help us solve problems.